All right, let's get into it. Today, we're literally digging into the ground beneath our feet. We're going to uncover the science of geotechnical engineering, and trust me, it's a wild story. It starts with some of the most jaw-dropping structures ever built, and it takes us all the way down to the tiny microscopic world of soil particles. So let's kick things off with one of the biggest engineering puzzles in all of history. I mean, just think about it for a second. We're talking 2750 BC, right? The Egyptians start putting up the Great Pyramids. Now, these weren't just pretty buildings. They were absolute geotechnical nightmares. How on earth do you support millions of tons of stone on nothing but sand and soil and not have it just sink or completely collapse? That single question, that's where this whole story really gets started. For thousands and thousands of years, building anything was pretty much an art form. It was a craft, right? Based on experience, a lot of trial, and a lot of error. But it's these incredible ancient challenges, things like the pyramids in Egypt or the dikes they built in the Indus Basin, that eventually forced us to develop a real science of the ground. Okay, now look at this timeline. What's absolutely wild here is the time gap. I mean, it's huge. We've got the pyramids starting way back when, and then crickets. For nearly 4,500 years, nothing. It's not until 1776 that a guy named C.A. Coulomb starts to even think about applying math, calculus actually, to figure out the forces inside soil. And even then, it took another 160 years for the top minds to get together at Harvard and officially create the field we now call soil mechanics. It's just an incredible delay when you think about it. So that big conference at Harvard in 1936, yeah, that didn't just happen by accident. It was all thanks to a handful of brilliant people who, and I'm not exaggerating here, almost single-handedly revolutionized how we understand soil in the 20th century. The main guy, the central figure, was Carl Terazaghi. He's known as the father of the field, and for good reason. He's the one who put that first conference together, and he literally wrote the book on soil mechanics. And right there with him, learning from the master, was Ralph B. Peck. He started out as Terazaghi's assistant and went on to become an absolute legend himself, teaching whole generations of engineers. And this quote, this just perfectly captures the spirit of the whole field. It comes from an author, Braja M. Das, who tells the story about meeting Peck at a conference. Get this, Peck was 93 years old, and he wasn't just sitting back. He was passionately explaining to people that engineering isn't just about formulas you memorize. It's about getting your hands dirty with field testing and, above all else, using sound judgment. Just incredible. Okay, so we've met the pioneers. Now let's talk about what they were so obsessed with, the soil itself. And here's the thing about soil. To really get it, you have to understand that our planet is running this massive, nonstop recycling program for its own crust. And it all kicks off right here with igneous rock. You can think of it as rock that's literally born from fire. It's what you get when super hot magma or lava cools down and gets solid. Believe it or not, every single grain of sand, every tiny speck of clay can trace its family tree all the way back to this stuff. So how exactly does hot goo turn into solid rock? Well, it happens through this process called Bowen's reaction series. It's kind of like baking, but in reverse. As the magma starts to cool, different minerals start to form at different temperatures. First up, the stuff that likes it really hot, like olivine. Then, as it gets a bit cooler, you get things like hornblende. And last to the party, at the coolest temps, you get the really tough, stable minerals like quartz. And that whole sequence, that's what decides what the final rock is made of. But that's just the beginning. It's all part of this huge loop called the rock cycle. So, that brand new igneous rock, the weather beats it up, breaks it down into tiny bits called sediments. Then, over millions of years, those sediments get squeezed together and become sedimentary rock. Now, if that rock gets buried super deep and gets cooked under intense heat and pressure, poof, it turns into metamorphic rock. And if it gets hot enough, it can melt all the way back into magma, starting the planet's ultimate recycling program all over again. It never stops. And how that igneous rock forms makes all the difference in the world. Let's look at granite versus basalt. Think of granite as the slow cook recipe. It cools way down, deep underground, over a long, long time. This gives big, chunky crystals like quartz plenty of time to grow. But basalt? That's the flash fry. Lava hits the surface and cools down super fast, leaving you with these tiny, fine grains. So you see, same basic ingredients, but completely different paths lead to totally different rocks. All right, so once rock has been broken down into soil, its journey is just getting started. It's not over by a long shot. And for an engineer, figuring out where that soil ends up and how it got there is absolutely critical. And soil is quite the traveler. It has a bunch of ways to get around. Giant glaciers can grind up rock and just dump it, creating glacial soils. Rushing rivers and streams carry it along, sorting it into what we call alluvial soils. You get lacustrine soils that settle at the bottom of quiet lakes, and marine soils deposited in the ocean. The wind can pick it up and blow it around, creating aeolian soils. And sometimes it just tumbles down a hill thanks to gravity. That's colluvial soil. The key takeaway here is that each trip creates a totally different kind of soil with its own unique personality. Okay, that was a lot of history and geology, right? So let's bring it all home. Why does any of this stuff actually matter when it comes to, building things? Let's connect all this science back to the buildings and bridges we use every day. Now just look at this number for a second. 15 square meters per gram. What does that even mean? Well, that's the typical surface area for a type of clay called kaolinite. And to put that in perspective, a single gram of this stuff, that's about the weight of a paperclip, has the same surface area as a small room. That's insane. That's the kind of mind-boggling, microscopic complexity that engineers have to deal with. All the tiny forces acting on that huge surface area are what control how the soil is going to behave. And that brings us to the whole point of this. Every single building needs a foundation. And what does a foundation do? It has one job: to take the entire weight of that structure and safely hand it off to the ground. But if you don't understand that ground, if you don't know its history, what it's made of, how it acts, you could overload it. That could mean your building slowly sinks over time, which is bad, or it could lead to something called catastrophic shear failure. That's when the soil just can't take the pressure anymore, and the particles literally slide past each other. The ground gives way, and the building goes with it. The stakes are incredibly high. So, for more than 100 years now, geotechnical engineers have basically become historians of the ground, learning to read the stories written in the soil. But here's the thing, our world is changing. We're building in tougher and tougher places, and our climate is shifting. The ground beneath us isn't a static history book. It's actively writing new chapters right now. And that leaves us with a pretty big question. What new stories and what new challenges is it going to throw at us next?